Okay, so the last topic in this overall lesson focuses on yet another scheduler operator that is used for RxJava reactive types. We've talked about a couple before. We talked about the new thread operator. We talked about the computation operator. And now we're going to talk about the I/O operator. And so this will be used to say, run this particular computation, these computations in the I/O scheduler. And this operator and the other ones we talked about, like computation and new thread and so on, work with flowable, parallel flowable, single, and maybe. So these are useful operators that kind of cross-cut the various reactive types in RxJava. So let's talk about the I/O operator. So this operator hosts a variable-sized pool of single-threaded executor service-based workers, which is just a fancy way of saying it's a thread pool. And it returns I/O, the I/O factory method, returns a scheduler that's designed for I/O-bound work. What the heck does that mean? Well, what that means is it's optimized for blocking operations. What does that mean? It means that it's really designed for tasks that are so-called I/O-bound and not compute-bound or CPU-bound and so on. And so one of the consequences of this is it will either start a new thread if there isn't any available thread, or it'll reuse an idle thread from a cache. So you have a cache of idle threads. So once they're started, they get stuck back in the cache. And when the next request for processing comes along, the I/O scheduler will first look and see, hey, is there any unused threads in the cache? If so, can I use them or use it? Yes, boom, don't have to create a new one. Otherwise, we'll go ahead and start a new one. So it works a bit like the cached thread pool that's part of the Java executor service. We haven't really talked a lot about that, but the executor service framework has a bunch of different factory methods that make different kinds of pools. The computation pool that we talked about before has a fixed number of threads, whereas the I/O pool has a variable number of threads, and it caches them. Excuse me. And why would you want to do this? Well, the reason you'd want to do this, of course, is because for I/O-bound operations, you're often wanting to be able to allow the thread to block for however long it takes for the I/O operation to complete. So you need to make it possible to add a new thread when another operation comes along that blocks, because otherwise you can underutilize the processing. So this is useful for doing blocking things like network calls, file I/O, database operations, and so on. And here's a simple example in the EX4 project in my Reactive Flowable folder in my live lessons repository that downloads a list of images from remote web servers in parallel and then stores them on the local computer. And we'll take a look at this. So basically, we use the from iterable factory method to get a list of URLs. Then we use the parallel factory method to convert the flowable into a parallel flowable. Then we're going to run this thing on the I/O scheduler thread pool. And then we have a method reference or a function or something called download and store image, which will download and store each image in the thread pool, the I/O thread pool. We then convert everything back to a sequential flowable, and then we collect the results into a list and print the results or do something with them. So that's basically the sequence of steps involved in using parallel flowable. Now, a couple other things to note. This particular thread pool is implemented using so-called daemon threads. We've talked about those before. That's the same kind of thread that we use for the computation thread pool. And they won't prevent the app from exiting even if its work isn't done. So if the last non-daemon thread goes away, then all the threads that are running in this I/O thread pool will also magically shut down. If you don't want that behavior, don't let the last non-daemon thread go away. And that's, of course, why for our test programs, we always have this main thread that uses the async task barrier framework in order to block the main thread till all the processing is done, because otherwise, if the main thread exited, all the other threads would go away. The schedulers Bounded elastic operator in Project Reactor is very similar in that it can basically add threads to this pool, and you can see that the underlying threads will be evicted if they're idle for more than 60 seconds, which again is very much like the cached thread pool that's part of the Java executor framework. Speaking of which, the Java common fork join pool is also quite similar if you use it with the managed blocker mechanism. So if you don't use the managed blocker mechanism, then the common fork join pool is more like the computation thread pool. If you do use it with a managed blocker mechanism and you're consistent in how you apply managed blocker, then you'll end up with a solution that basically works like the I/O thread pool does in RxJava. Okay, so that's the end of that particular example, discussion rather, that lesson about the I/O scheduler. So now you're in very good shape to be able to do assignment 4B because we've talked about all the different pieces you need to know in order to be able to modify 4A, which is the one that used the flat map concurrency idiom, to use the parallel flowable technique that we've talked about here together with the I/O scheduler.